All right, let's jump right in. Welcome to the Ultimate Explainer. If you're gearing up for the CEE 2083 exam, or honestly, if you just want to totally master the foundations of early modern physics, you are in exactly the right place. Today, we're cracking the subatomic code. We are going to break down the monumental discoveries of cathode rays, positive rays, and the electron. I'll be giving you the conceptual anchors and the exact exam shortcuts you need to completely dominate this topic. So let's get started. Think about it for a second. How on earth do you weigh a particle you literally can't even see? It's kind of the ultimate historical mystery, right? See, before the 20th century, atoms were thought to be these solid, indivisible blocks, the end of the line. But then, some really anomalous things started happening in laboratories. Scientists began to realize there were invisible building blocks making up the universe. But how do you measure, weigh, and calculate the speed of something that is invisible to the human eye? Well, to solve this subatomic detective story, scientists had to build a very specific kind of trap.
Okay, let's dive into this. Section 1. Inside the glass tube, the subatomic mystery begins.
To actually coax these invisible particles out of hiding, scientists needed a pristine environment, a sealed glass tube. Inside this tube, we have two metal plates, the negative cathode on one side and the positive anode on the other. Now, they're hooked up to a massive high-voltage supply, but the real magic? That happens because of a little vacuum pump nozzle at the bottom. By systematically sucking the gas out of the tube and dropping the pressure, scientists began peeling back the layers of reality, revealing phenomena that had literally never been seen before.
Now listen up, because this pressure drop sequence is a highly tested concept on the CEE. As we pump gas out, the inside of the tube goes through some wild changes. At 10 millimeters of mercury, you get these blue zigzag sparks and a crackling sound, almost like miniature lightning. Drop it to 5, and the sparks smooth out into a steady, beautiful colored glow. And remember, that color depends entirely on the specific gas inside. But keep pumping that gas out. Down at 0.5, a mysterious dark void called Crookes dark space appears. At 0.02, that dark space fills the entire tube. The gas totally stops glowing, and the glass walls themselves begin to powerfully fluoresce. Finally, at 0.01 millimeters of mercury, the tube goes visually dark inside. But, and here's the kicker, an invisible stream of energy is rocketing across it. Cathode rays are born. So what exactly is happening at this stage?
Moving right along, Section 2, Catching the Electron.
We need to myth-bust a major CEE exam trap right now. Because they're called cathode rays, exam writers absolutely love to trick you into saying they're electromagnetic waves, like light or X-rays. They're absolutely not. Cathode rays are physical, material particles with mass and a negative charge. We know them today as electrons. They shoot out of the cathode like tiny bullets traveling in straight lines at up to 1/10 the speed of light. And because they're physical objects carrying kinetic energy, if you slam them into a heavy metal target like tungsten, they suddenly stop. That massive braking energy actually converts into X-rays. Finally, note that last point. It's absolutely crucial. They have a universal charge-to-mass ratio.
Now, what's really interesting about this is how we figured out the exact charge of these tiny bullets. For that, we look to Millikan's famous oil drop experiment. Millikan sprayed microscopic drops of oil into a chamber and used X-rays to give them a negative charge. He then adjusted a uniform electric field to pull the drops upward, directly fighting the downward pull of gravity. By measuring the speed of the drops falling freely without the field, using Stokes' law of fluid viscosity, and then comparing it to their speed when the electric field was pulling them up, Millikan was able to calculate the exact charge on a single invisible electron.
And from that oil drop experiment comes this massive conceptual anchor for your exam, the quantization of charge. The formula is Q equals NE. Millikan discovered that the charge on every single oil drop was always a whole number multiple of 1.6 times 10 to the negative 19th coulombs. It was never, ever a fraction. You can't have 1.5 electrons worth of charge. It's kind of like buying eggs, right? You can buy 1 egg or you can buy 2 eggs, but you can't buy 1.3 eggs. Charge always comes in fixed, indivisible packets. Which brings us to this incredibly specific number, J.J. Thomson's specific charge, or the charge-to-mass ratio of an electron, 1.76 times 10 to the 11th coulombs per kilogram. Here is your major exam shortcut. This number is a universal constant. Exam questions will constantly try to trick you by asking, hey, what happens to the E over M ratio if you change the gas in the tube from hydrogen to neon, or if you swap the cathode from iron to copper? The answer is always nothing. It stays exactly the same. Electrons are identical everywhere in the universe. They really don't care what gas or metal they came from. But wait, if atoms are naturally neutral and we just knocked a bunch of negative electrons out of them, what happens to the leftovers? That brings us to Section 3. Enter the positive rays.
So, when those super fast cathode rays smash into neutral gas atoms, they literally knock electrons completely out of orbit. The gas atom is now missing negative charge, making it a heavy positive ion. To really grasp how these positive leftovers behave, I want you to use this analogy. Cathode rays, the electrons, are like fast, light bicycles. They zip right past other atoms, penetrating deep, but they have relatively low ionizing power because they're just so small and fast. Positive rays, on the other hand, are the massive nucleus left behind. They are like slow, heavy bowling balls. When they move, they don't penetrate very far, but they crash violently into other atoms, causing massive ionization. Eugene Goldstein actually proved the existence of these positive bowling balls using a perforated cathode, essentially a negative plate with holes drilled right through it. While the tiny negative cathode rays shoot left to right toward the positive anode, those massive positive ions created in the gas are heavily attracted back toward the negative cathode. So, they flow backwards. And because they are so heavy, they build up incredible momentum, acting like heavy trucks driving straight through the holes in the cathode to the other side, forming what he called canal rays, or positive rays.
All right, home stretch. Section 4, deflection, flight paths, and exam traps. So, we have our particles, now we need to control them. This right here is your ultimate cheat sheet for calculating how charged particles move when subjected to external fields. This makes up a massive portion of the CE. Mathematically, a particle's velocity is proportional to the square root of the voltage. Why? Because the kinetic energy given to a particle equals its charge times the voltage. 1/2 mv squared equals q times v. When you do the algebra and solve for velocity, the voltage ends up trapped under a square root. Do not fall for the trap of thinking it's a simple 1-to-1 ratio. If an exam question asks how to double the speed of an electron, you cannot just double the voltage. Because of that square root, you actually have to quadruple the voltage power just to get double the speed.
And this brilliantly illustrates what happens when you fire one of these charged particles into a magnetic field. You have to memorize these 3 geometric flight paths. Step 1, if a particle enters perfectly parallel to the magnetic field at exactly 0 or 180 degrees, it feels 0 magnetic force. It just sails straight through, totally undeviated. Step 2, if it enters exactly perpendicular at 90 degrees, it gets entirely trapped in a perfect circular path. Step 3, if it enters at any oblique angle, say 45 degrees, it actually does both. It moves forward while spinning, creating this helical or corkscrew spiral path.
Let's actually visualize that crucial 90-degree entry for a second. When the particle's velocity enters the magnetic field, the resulting magnetic force acts perfectly perpendicular to that velocity. Because this force is always pushing inward at a strict right angle, it acts as a centripetal force. It can't speed the particle up, and it can't slow it down. It can only continuously steer it, locking the subatomic particle into endless, perfect circular motion. This is exactly how massive particle accelerators and mass spectrometers control subatomic traffic. Which brings us to the ultimate question. In these old glowing glass tubes, we isolated the invisible building blocks of the universe. We found the fast, light electron and the heavy positive ion. But listen, these aren't just historical curiosities. These exact principles, shooting electrons at tungsten to make X-rays, using magnetic fields to steer them in perfect circles, these are the very foundation of modern medical imaging, the screens we stare at every day, and even the cutting-edge quantum computers of tomorrow. We learned to weigh the invisible, but the real question is, how will you use these subatomic tools to shape the future? Keep reviewing these core principles, watch out for those tricky exam traps, and I'll catch you in the next explainer.